Thank you very much. So the agenda is pretty straightforward. Get into details of HBase and also look at some operational issues or metrics and monitoring. That's pretty much it. How many people here know about HBase or big table? Oh, okay. So it's based upon the big table paper out of Google. And how many people visited the booth outside from Bloomberg to see what it can do and what it can't? Okay, excellent. So, and also one other question is, who attended the yesterday's session about distributed systems, elements of distributed systems? Okay, not many. I just want to say that you can relate to that talk when you see what some of the concepts being implemented in HBase. So that was the idea. So before we get into the HBase details, I just want to give some context about why HBase in Bloomberg. So as you might have seen in the terminal, the Bloomberg terminal, which serves wide array of information for financial decision making. Wide array of information means wide array of data being sourced from different sources. To give an example, you have ticker data, which is the market data coming in, which is, and on top of it you can get news. There are data coming from location about tankers around the world. It's a cool thing, you can go and check it out. And also data from tweets to give you sentiment analysis. So just give you a sample of data variety we pull in to give information in the terminal. So the key is on all this, since it's all used by the financial decision makers, the key is to be able to give this data at low latency and high availability. That's no compromise on that one. So that's the key. So the reason for HBase and some of the other distributed platforms we adopted within Bloomberg is primarily because they have the capabilities to store a lot of data. On top of it, it is highly available and low latency. So that was the primary reason we had used HBase and some other distributed systems within Bloomberg. So now let's get into details of HBase, and we have been using HBase from 0.94, and this is a little old, but at least you can see that we have billions of queries being executed on HBase with millisecond latencies. So that's for some of the use cases what we have, and some of the data being showed right now on the terminal. And also just want to point out that we also contribute to HBase and also some of the open source applications like systems like Spark and Kubernetes and whatnot, because somebody was saying that Bloomberg is primarily C++, but it's not the case, because a lot of the information what we derive, we use the cutting edge open source systems what's available out there. Okay. So next, I'll just walk through to some of the basic principles of HBase to give some idea about what HBase is, and also give some terminologies which is common in HBase. At its core, it's an ordered key value store, and it's distributed. So that's at its core. What that means, let's try to unpack it. So when you create a table in HBase and try to write data into it, all the values are stored as a key value pair. Is persistent inside on the files. So this is like just an example, and it's all ordered. So in the case, it's lexicographically ordered, and the term we use for a set of key value pairs, which is kind of a shard, is a region. So bear with me, so it will make sense when I go through it. So we have key values that are persisted for each of the puts, which is called the writes, and they are ordered. And a shard or set of rows or key value pairs is called a shard, is called a region. So as more and more data gets written, what happens is HBase automatically splits a region and creates two regions, for example. And the regions, how it splits, can be defined by the user. So by default, it says it's a fixed size region. So if the region size is set to like 10 GB as the size, so once the region grows to 10 GB, then HBase just splits and makes into two regions. So as it goes along, more and more data is written, and multiple regions get created, and then they get distributed. and the servers which handles the regions are called region servers. So as you can expect in a distributed system, there are multiple nodes, and these shards get distributed along as the data grows, and they are called region servers. Are we all with me? Any questions so far? Okay. Now let's take a little bit of details into the key and the value. So the key consists of a row ID. The row ID is nothing but a user who sets a value for a row, identifying a row. So if you think about the RDBMS, it is nothing but a value for the primary key, say, right? So you set a row ID, and the next value which is used for the key is the column ID and a timestamp. So they constitute together as a row key or a key, and the corresponding value is the value for that column in that row. Does it make sense? So from the user perspective, if you write a row R11, say, and there are 4 columns, you can see how it gets persisted on the file. So there will be multiple key value persisted on the file. So even though from the user perspective you have one row with multiple columns and values, behind the scenes on the storage, it just creates multiple rows for the key value pair. And as I said before, you can the time value, the timestamp which is used in the key is used to help with the versioning feature. So as more and more data gets written, the timestamp get incremented. Like for example, in this case, you can see that column 1 has got 2 rows, two key values, but one is having a higher timestamp than the previous one. That means you had a latest update to that column value for that row. So when a person or when a user queries for a column value for R11, by default it picks up the latest version of the key value and then returns to the user. And HBase also provides grouping of columns. So I think yesterday when we talked about the distributed systems elements, you have called the columnar format. So it's not totally columnar format, at least you can get a feature of storing related columns in a storage behind the scenes. So for example, you have 3 columns, you want to group it because it's all normally called together or used together by the user. So it can be grouped and then stored into a single file, and as another set of columns for the same row can be stored in a different storage or different file behind the scenes. So when the user calls only the first set of columns, only the data from the first set of files will be returned to the user, but the other set of values, which is in a different set of columns, will never get pulled into memory. So it will make sense when you go further a little bit more. So this is a feature there where you can group columns into column families. Right. For RDBMS, people who who understand RDBMS, just to give an overview on the acidity, there's no cross row level transaction. It's just on a row level. Only the current row which you are working on has as atomic. Like if you're mutating one row column, sorry, if you're mutating one row, that's fine, but you can't expect that there's going to be a transaction across rows, like in RDBMS. And consistency, it maintains consistency on any data being read to be consistent from the time in the past. Like if you are making a query now, and the data will be consistent to a point, let's say minus X, that's not determined, because that point in time it will be consistent forward, because if there is any updates happening at this time, it will not be reflected. So it will assign a time value before the read happens, and then the value which in return will always be consistent for you. Isolation on the mutation level, on the read level, as I talked about, you have time set so that anything after the time it's going to be consistent. For the mutations, it takes a row lock and gives you, that means only one mutation can happen on a row at any point in time. And from the durability perspective, if a put or a write happens and if it's been acknowledged by HBase, then that will be durable. So just to this gives you just overview of some of the terminologies and the basic concept. Let's see how it's been implemented. Before going that, there's one more thing I want to touch base on is like the DBMS, RDBMS, it gives you the facility, HBase gives you the facility to group tables into namespace, like a schema, if you can think about in RDBMS world. And also it gives you to set access control at different levels, on the namespace level, on the table level, on the user level, and whatnot. So let's dive deep into the read and the write path. So when a read comes in, the read is, when the write comes in, the write is taken by a region server, because as we talked about, the region server is the one which knows which region that write has to go to. And then the first order of action would be to write that writes into a wall, which is a write ahead wall. That's for durability. And once that is done, then it writes into an in-memory data structure called memstore. As the data gets written more and more, say it is always affecting the same region, say for this example, the memstore gets filled up, or there are criteria which determines the memstore has to be flushed and files has to be created on disk. So the memstore, so as more and more writes happen for the same region, so more store files get created on disk. And the store files, if you look at the structure of the store files, they are made up of blocks. They have data blocks, index blocks, and Bloom filters. Bloom filters is to determine that when you're doing a read, the Bloom filters give the flexibility of skipping some of the files, because Bloom filters will say, hey, this file doesn't have the rows for these columns, these requests which is coming in. So that's the purpose of Bloom filters. And also, HBase, even though it just writes, it depends on the underlying file system to give it the data availability. So for example, if you're using the local file system, like normal Linux file system, if the region server which is hosting that data, region, and if there's a file system crash, then that data is lost. So normally in production scenarios, you would want to use something like HDFS, right? So in this case, in our installation, we use HDFS, and it uses the DFS client to write data. So what happens is, it uses DFS when they write the wall, or whenever it does the memstore flushes, it talks to HDFS. The component in the HDFS is called data node, which then replicates the data so that if there's any failure in one node, still the data is available for HBase to use. So that way, the data is highly available. So as and when more and more flush happens, as you can see that updates for a key has happened. So that means whenever the flush happens, the key value is in different files on the store file. So what will happen is, when you have a read, then it needs to go through the different files to give you the data back. And also the deleted data also sits in different files for that corresponding region. So in order to improve the performance of that, HBase has a process called compaction. So there are two types of compaction, minor compaction and major compaction. The minor compaction, what it does is, it constantly runs and it looks for criteria like smaller files less than certain X size. It just tries to merge it and make it into a larger file. And once the size of the files goes beyond a limit of X set, then it has to wait for the major compaction to run. So what will happen is, when the major compaction runs, it will remove all the deleted data and also try to merge values for the keys, and then they create a larger file. So that means when the read comes through, then it has to only scan through one of the files to get the data back. And it uses the index and Bloom builders and whatnot to identify the location quickly. So that's on the compaction perspective. Now let's look at the read. So from the read perspective, assume that we made a request for table row 1, and then it identifies, the HBase client identifies which region server hosts that region, and then it goes and then pulls the block from the store file and then first stores into something called a block cache, which is kind of the read cache. And then once it's brought into the block cache, and it checks for the memstore to see any update happened recently for that row. And then it merges together and then responds to the query, right? So in case of HDFS, what will happen is normally when the DFS client asks for data, it talks to HDFS and then it uses TCP to communicate to get the data back to HBase to use. So one nice thing in HDFS is that there is a feature called short circuit read. Once you enable it, what will happen is if the data for that corresponding key or the corresponding region is on the data node on which the region server is executing or running, then it will give back the file descriptor and then the read happens locally. So in a typical installation, the region server and the data node all on the same machine, so that if the data is available on this machine where the region server is running, and the HDFS would say, hey, now you can use the read locally from the machine, and it gives a good performance improvement for your reads. So that's something we have leveraged for our low latency application. The next one is, given that nowadays the machines are coming with larger memory, one of the things you would want to do is to increase the block cache size, which is the read cache. But at some point when the cache size is increased, the flip side of that is that you will have GC process taking more time. So that means if you are you're latency sensitive, then what happens is the tail latencies may be higher, something that may not be acceptable to you. So one of the features in HBase is to be able to create cache off heap. Off heap means that it's not on heap, it uses the direct memory, Java direct memory to use it. So that way you can allocate a larger size of off heap memory, and that acts as an L2 memory, which is kind of, if you look at hardware, you have L1 memory and L2 memory. So the default block cache is L1, which is on heap, and the L2 off heap. So from the read perspective, it pulls first back into the off heap cache and then pulls into the block cache, looks at the mem store if there's any update happened for that row which has been requested, and then sends it back. This is based upon 1x series of version 1x of HBase, but in 2.0 even the L1 cache and becomes off heap as well, so that the performance will be much better. So we are looking forward to that. And even in 3.0, I think the mem store, which is the write cache, is also going to be an off heap hash. So we talked about all these regions and region servers, and you have multiple region servers. How do they all get coordinated? And that's, and that's the role of HBase master. So it's kind of the coordinator. So and also the HBase master creates its own tables, the system tables, to keep track of metadata, like the objects created, the regions, and also the ACLs, what is set for each of the regions, the namespace and whatnot. So it keeps in the system table. So in order for the HBase, because now we have multiple region servers, but in order to make the master to be not a single point of failure, you can have multiple HBase masters. So then what that means is, how do we know that who is going to be the master, and if one master goes, who is going to be, how the other one would know, and then how it will take over the master, right? And that's when Zookeeper comes into play. So Zookeeper is used to coordinate. So whoever the master, it takes a lock on it, and the other ones would watch on the lock, and then once the current master fails, then the Zookeeper would give a notification and the other one would take over as the master. Okay, who else is used in Zookeeper? All the region servers also use the Zookeeper. Whenever they come up, they also register into Zookeeper and say, hey, I am live. And if one of them goes down, the Zookeeper would notify the master that the region server goes down. The region server is not available and it's not part of the cluster anymore. Okay, who else? Even the HBase client, the application which it uses, who wants to understand the cluster, where things are, it again needs to know what the Zookeeper quorum, which is used by the cluster as well. Okay, let's look at what happens in a region server failure scenario. So the HBase client comes and asks for a row R1 for a table T1, and the region corresponding to that is in region server 6. And for some reason, when the query came in, the region server went down. So what will happen is, when the region server goes down, the session with the Zookeeper goes down, and then HBase master gets notified that this region server goes down. Then it reassigns the region from RS6 to RS4. Now the client can go to RS4 and get the data back. So that means it involves a lot of steps and it takes more time. So that's again from the latency perspective, it was not very helpful. And there's a feature in HBase which you can enable called region replication. So when you create a table, you can say, I want not only one region, the regions of that table has to be replicated to other region servers as well. So what will happen is HBase master will say, okay, this is the primary region and this is the secondary region. The primary region or the region server who holds the primary region would always be the one who gets the updates or the writes. And the writes which is happening in this case RS6, which we consider as the primary, any updates happening, it gets shipped on to RS2, which is the secondary as well. So there's a small lag. So in this case, when there's a failure, HBase client can make a secondary call to the second region server where the secondary data is secondary region is being deployed. So the request goes to let's do the same scenario. The request goes to the RS6 and there was a failure, and then the HBase client can directly go to R1, which is the row 1 on RS2. The only criteria there is always a lag between the updates happening on the first region server to get populated to the secondary region. So what it would need is the HBase should always say, hey, if there is a stale data available, I am happy to take it. So that is one criteria you need to set on the application side. And it's in milliseconds, but if you are concerned about that delay, then you will not be able to leverage it, but otherwise you should be able to leverage this feature. Given the link to a YouTube presentation to look further about the whole process and the timing of it. Okay, now we have a lot of region servers and a lot of regions. How does HBase make sure that the cluster is utilized appropriately? Because it needs to be using all the region servers in the cluster, and how does that happen? So the HMaster has something called a balancer and an assignment manager. So to give a quick example, the balancer, the HMaster knows what regions are where, and it collects metrics about the cluster itself. So every region, how much request goes to a region, and how many regions are there in a region server and whatnot. So let's take an example of region servers having, there are 10 regions in the cluster, and there are 5 region servers. So then the master would look at and say, hey, how much regions has to be deployed on each region server? So it is 2 per region server, but it sees that there's not many in this case. There are 2 region servers which doesn't have the regions. So what it does, it just tries to create a new configuration of the cluster in itself and says, okay, now let me see whether I can come up with a new cluster configuration. And if the cluster configuration says that now it is more balanced, more regions are assigned to different region servers, then it just assigns the regions to assigns the region servers to all the region servers. Sorry, assigns the regions to all the region servers. So these are all some of the factors it looks at to come up with the to balance the cluster in itself. So and also it takes into consideration the move cost. If you have to move a region from one region server to other region server, it also considers the cost of that as well before it tries to balance the cluster. Some of the other features I'm not going to cover is HBase replication. So if you have 2 clusters, you want to replicate data across the clusters, you can use the replication feature. And also multi-tenancy support. If you have multiple tenants using a cluster, there are features in HBase. We can say, hey, this set of region servers can be used by this tenant, and this other set of region servers can be used by another tenant. So you can look at all the details there. And also co-processors and filters which can be developed by users, which is nothing but similar to the store procedures and triggers. You can write code and which can execute within the region server itself. So, but there are some gotchas. You may want to look at the details of that. So this is from the operator view. This is how it looks. So the name node is just the master for the HDFS, similar to the HBase master for HBase. And as you can see, the zookeeper is critical because zookeeper is used by name node or the HDFS as well as HBase master. So in order for the application, the cluster to be live and to be able to service high availability, you may want to look at the availability of each of these components. So it's not only HBase, you need to look at the totality of the whole cluster itself. So from the zookeeper perspective, we want to make sure that there's a quorum available. So there are a few commands which is available in zookeeper, something called stat. The stat gives you, if you run a stat command against a zookeeper instance, it will tell you whether it's a leader or a follower. So you can make sure that at least one zookeeper instance in the whole cluster, the zookeeper cluster is a leader, and at least we have multiple followers, which forms a quorum. And also what we do is we also run constant tests against zookeeper, say list for z nodes to query the z nodes in a zookeeper cluster. So if you are able to return the data from a z node, then that means the zookeeper is available. So that's something you can constantly run, and if there's any failures there, you can just send a notification to make sure that the zookeeper cluster is not available, and then take action on it immediately. From the HBase availability perspective, HBase also publishes a lot of JMX metrics, and it's all available on the master node, and that would be normally the URL for the master node JMX metrics. And the key metrics you want to look at is to make sure that at least one master is active. So that is the first one. You want to look at the dead region servers in the whole cluster which is reported onto the master, and depending upon your size, you can set criteria about how many are there, and you can set the criticality of your of the issue, or you can raise you can send tickets to yourself. And then the last one is the region in transition. So when HBase assigns regions as part of the balancing, sometimes regions get stuck, and we want to make sure that the regions are not in transition for a long period of time. If they are stuck in long period of time, there's an issue. That means if there's a query which goes to pull data from that region, then they will not be serviced properly. So that's something to monitor as well from the availability perspective. And last but not the least, you want to run some constant tests to query the list of tables, just to make sure that the metadata is available, and if it fails, you need to be able to notify immediately. Same way with HDFS availability, the master node or the name node has JMX metrics, and we want to make sure that at least one is active. You want to watch for data nodes, which is where the data resides. Missing number of blocks, if there is anything we want to understand, if there is the percentage of use by HDFS, you want to keep to a limit so that it doesn't go beyond a certain limit, and then you have a problem. Under replicated blocks as well, you may want to look at that and make sure that they are not greater than 0 or not for a long time. And then you can run tests for availability, the HDFS. This is just for the availability perspective. You should get notified, but from the performance and the capacity planning perspective, you may want to collect data from the JMX metrics from the region servers, and all these metrics are available on the region server level, region level, and the table level. So once you have it, you should be able to understand the pattern, and also the if there's any issues, you can go back historical details and see if anything has changed and whatnot. From the JVM perspective, you may want to look at the garbage collection timings, and again it is published through the JMX URL for all the services, so you should be able to send it. And also you may want to enable the GC logging, something to look or do some analysis if there's a problem there. And as usual with all the metrics from the OS level for memory, CPU, disk, and networking, that again helps you to debug issues. Recently we've had a problem. One of the issues we found out there's a high latency. We figured out that the problem was with soft IRQ CPU usage is very high, which in turn we figured it out that it was a problem with an array controller's firmware issue, so we had to upgrade it. So just to keep that in mind, so you can collect all this data to get debug issues like that. And the last, all these processes writes into a logs. You may want to consolidate into a single place. And since it is humongous, so you may want to filter it down so that you have critical data in a single place so that you can go back and see what kind of errors and issues being logged by these instances. Finally, from the HBase perspective to interact, you can interact with the shell. You can use admin API to automate some of the processes you would do to manage these clusters, and from the client APIs for to do the gets and the puts and whatnot from the application. And last but not the least, as a database, you would not want to leave any discussions without knowing how to back up and restore data. So you have you can take snapshots, you can restore snapshots. If you want to move data from one cluster to another, you can use the export snapshot tool, and also you can do a copy table tool which can take a time from this time to next, like a start time to end time, so you can get a subset of data to be copied from one cluster to the other. I think that's pretty much I got. I just want to thank the HBase community, and if you guys, I think you should, if you're interested, you should follow the community. It's a pretty cool set of people to work with. Yeah.
I have one question. So you said that, I mean, HBase uses HDFS, right? So when you're using the second region, why do you need to write in the second region? You already have the HDFS, which takes care of.
Oh, okay. So region in the HDFS it is duplicated, but somebody needs to service. From the HBase perspective, somebody needs to service that region. The data is not copied. The region is assigned, but still the data is the single copy of the data.
Oh, it's a single copy of the data.
But the only thing is one more region server would be able to service the data.
Then there is no question of replication lag. You said there is a delay between the regions, right? So
oh, because
if it is written only once.
But there is some data still in the memory, right?
Okay.
You understand what I'm saying? It's not just the flush. You have real-time data, like as I talked about, you have writes happening on the mem store as well.
Okay, then if it is like if you're going with the ACID compliance, then everything should be flushed to the disk, right? I mean, if the node that is having the memory goes down, then the data is not consistent, right?
If the no, it's written in the wall. If there's any failure, then the wall get replayed so that it will get the data from the wall.
Okay, but we won't get it on the other region.
Yes. So there will be always a lag in the other region.
Okay, got it.
Make sense?
Thank you.
Okay.